Okay, so in this video we're going to talk about intermolecular forces, or IMF, and there's really three intermolecular forces that we can possibly have. One of them every compound is going to have, and that one is London dispersion. Now, what London dispersion is just an induced dipole, so that means that it happens instantaneously, and this is only significant only when molecules are very close to one another. Okay. The next one is called a dipole-dipole interaction. Now, a dipole-dipole interaction is when we have an interaction with polar molecules. Now, for molecules of approximately equal masses and size, the strength of the intermolecular attraction increases with increasing polarity. So if it's very polar, the intermolecular forces are going to increase as well. And the last one, hydrogen bonding, traction of hydrogen atom attached to a highly electronegative atom, that's either fluorine, oxygen, or nitrogen, and a nearby small electronegative atom in another molecule or chemical group. We really see a good example of hydrogen bonding happens with water, because all we have is oxygen and hydrogen in there. The oxygen is a highly electronegative atom, and what's going to happen is that there's going to be an attractive force between the hydrogen from this water molecule to the oxygen of this water molecule and back forth, and we get this network of hydrogen bonding with water molecules, and that's what causes water molecules to kind of pull one another together. We see if we were to pour water on top of a surface area, it just doesn't run everywhere. It actually domes up and it pushes against things. That's why some insects are able to walk on top of water. Now, if we're going to compare intermolecular forces, when molecules of two substances have comparable molecular weights and shapes, dispersion forces are approximately equal in the two substances. So as the intermolecular forces get stronger as molecular polarity increases, hydrogen bonding has the highest interactions. And two, when the molecules of two substances differ widely in molecular masses, and there is no hydrogen bonding, dispersion force tends to determine which substance has a stronger intermolecular attraction. So intermolecular forces are higher in compounds with higher masses. So let's kind of look at some examples of figuring out what kind of intermolecular forces we're going to have. So our first one, propane, C3H8. I'm just going to draw the Lewis structures. Okay, now this one we just have carbon bonds, carbon to hydrogen bonds. All three carbons, the shape that they're going to have is tetrahedral. And if we were to find out what kind of bond it was going to be between carbon and hydrogen, it's going to be non-bonding. So this is a non-polar molecule. Let me zoom in a little bit. All right, so since it's a non-polar molecule, the only intermolecular force that we have going on with this one is London dispersion. Okay? Because since it's non-polar molecule, we won't have any dipole-dipole interactions, and we won't have any hydrogen bonding going on either. Now, let's look at dimethyl ether, CH3OCH3. Okay, so here's the structure. This will have, the carbon and hydrogen we said would be nonpolar, but with the carbon and oxygen bonds, it would be polar. And it's asymmetrical, so this is a polar molecule. So intermolecular forces, we have London, and we also have dipole-dipole. Next one to look at is acetaldehyde. This is how this is set up. Once again, we are going to have a polar bond between the carbon and the oxygen, and it is asymmetrical, so this is a polar molecule. We're going to have London and dipole-dipole. Excuse me. And the last one is acetonitrile. We'll talk about Vesper shapes with these when we get back. Okay, so nonpolar, nonpolar, carbon and nitrogen, polar, asymmetrical, so this is a polar molecule. London, and also dipole-dipole. None of these would have hydrogen bonding because the hydrogens are not bonded to a highly electronegative atom, so it's not bonded to oxygen, nitrogen, or fluorine. If you look at these, I also put down the boiling point. So for propane, the boiling point is 231 Kelvin, dimethyl ether, 248 Kelvin, acetaldehyde, 294 Kelvin, and for acetonitrile, sorry, I need to move that up, 355 Kelvin. Now, why does the boiling point increase throughout these types of compounds? Okay, well, first of all, why does propane have the lowest boiling point? Well, since it's a nonpolar molecule, it's not going to have that large enough intermolecular forces or intermolecular attractions to cause the compounds to be closer together. So that's why its boiling point is a lot lower than the rest of them. Now the other three, polar, 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 they all have London and dipole-dipole intermolecular forces. But why is acetonitrile boiling point 355 Kelvin? The other two are less than that. It deals with the bonds that we have in it. So if we look at the dimethyl ether, between the carbon and oxygen we have a single bond. The acetaldehyde, we have a double bond between the carbon and the oxygen, and the acetonitrile, we have a triple bond between the carbon and the nitrogen. With bonds, the single bonds are the longest, and they don't have that, out of all three of them, they have the lowest amount of energy. Double bonds right in the middle, triple bond, shortest, has a whole lot of energy. Okay, so when we start making multiple bonds, that's going to start kind of increasing the polarity if it is a polar bond between the two atoms. So since this is a short length triple bond, it has a lot of tendencies to be more polar. And another way that we can figure this out is if we look at the dipole moment. And when we come back, we see each other again, we'll look at that because that's more calculations, and I'd rather do it up on the board so you can kind of see how things are going to go with that. All right, now let's look at two compounds that we do have hydrogen bonding. Okay, so we have acetic acid, and let me draw that out real quickly. Just draw the Lewis structure. And we have propanol. Let me start that. 3OH. So you can kind of see where the lone pairs were at. All right, there we go. Now, if we look at the boiling points in these two, acetic acid has a boiling point of 391 Kelvin. Propanol is 370. If we look at them, if we calculate out the masses, both of these are very close in mass. Kind of going back to these, all four of these are roughly close to one another in mass. Okay? Now, why is acetic acid's boiling point higher than propanol? Okay, well, they're both polar, as I said. Let's So the IMS will have London, dipole for both of them. And with both of them, they're both going to have hydrogen bonding. The difference is that with the acetic acid, since it has this C double bond O, this oxygen, it has more tendencies to have more hydrogen bonding going on than with the propanol, where it just has the one oxygen. So 2 points of where we can have hydrogen bonding happening at, that's going to cause our boiling point to be higher than where we have only 1 point of hydrogen bonding to take place. Okay? So with your Vesper packet, try to go through, try to figure out what kind of intermolecular forces everything's going to have. And when we meet up next, we will talk about it, we'll go over it and explain the reason why. If you have any questions, please email me. Thank you.